Hello everyone, welcome back to the channel. In today's tutorial, we're going to learn how to perform flood hazard mapping using Google Earth Engine. So before we jump into the code part, it's very important to understand the complete methodology behind this project. Understanding the workflow is much more important than memorizing code. So the poster summarizes the entire flood hazard mapping progress, and from collecting satellite dataset to producing the final flood hazard map. Once you understand this workflow, the code becomes much easier to follow. So uh, the title of the poster is flood hazard mapping. So flood hazard mapping is a process of identifying areas that are more likely to experience flooding based on the environmental conditions. Notice that I have said the hazard, not the flood protection. So these two terms are different. So flood protection tells us when the flooding may occur, and flood hazard mapping tells us where the flooding is more likely to occur. So this is very important distinction. Below the title, you can see the subtitle, Multi-Criteria GIS and Remote Sensing Approach. So the phrase multi-criteria means that we are not relying on just one factor. Instead, we combine several environmental indicators together to estimate flood susceptibility. So in real life, flooding depends on many different factors that could be the distance from river, elevation, terrain shape, and vegetation, and many others. We will use the integration of hydrogeomorphic, topographic, and spectral indicators in Google Earth Engine to assess the relative flood susceptibility. So I have used the hydrogeomorphic over here. Hydro refers to water, and when we talk about geomorphic, refers to the shape and the physical characteristics of the Earth's surface. Together, hydrogeomorphic factors describe how water interacts with the landscape. And then the topography simply means the elevation and the shape of the land. For example, the mountains, valleys, plains, depressions, all these things influence how water will flow. And we will also use some of the spectral indicators like NDVI and NDWI. And we're going to use Google Earth Engine. Instead of downloading hundreds of gigabytes of satellite images to your computer, the analysis is performed on Google's cloud server. So let's discuss the data sources. Now let's move to the major section of the posture, the data sources. So every flood hazard model depends on the reliable dataset. In this workflow, we are using four main datasets. The global surface water. This dataset is produced by the Joint Research Center of the European Commission. It shows where the water has been observed over many years using satellite imagery. So instead of showing water only one date, it tells us how frequently water has occurred at every location. And then we have used SRTM DEM. The second dataset is this, and the DEM stands for the digital elevation model. So a DEM represent the height of the Earth's surface. Instead of photographs, each pixel store elevation values. The dataset has a spatial resolution of 30 meters. We are using the spectral indices like NDVI and NDWI. So we're going to calculate all of these indices using this dataset. And then we have the Google Earth Engine, a platform where we perform all of that. Okay, now let's discuss the methodology for workflow. So this section summarizes the entire flood hazard workflow. So the step one is the water occurrence. We begin by identifying permanent water bodies using the global surface water dataset. Pixels with a very high water occurrence are classified as a permanent rivers or lakes. And in the step two, we have the distance from river. This is really simple. Next, we calculate the distance from every pixel to the nearest permanent water body. So the closer allocation into the river, the higher is flood susceptibility. The farther away, the lower the flood risk. It's simple that. Then we have elevation. Elevation using the DEM, lower elevation receive a higher hazard score, become flood water naturally flows downhill. And the step four, we have the topographic position index. So TPI helps distinguish valleys from ridges. Valleys receive higher flood score because water accumulate here. And the step five, we have the vegetation, NDVI. So NDVI areas covered with the dense vegetation receive lower hazard score. And the reason behind this, because vegetation slows runoff and increase water infiltration. So bare land receive higher score. And then we have step 6, NDWI. Finally, we calculate the surface wetness. Already wet areas receive higher flood hazard score. And then we have the criteria and the scoring. Like we are this is one of the most important part of the methodology. Instead of keeping every data set in its original units, we convert them into a common scale. And why we are doing this? Because distance is measured in meters, elevation in meter above sea level. NDVI ranges from -1 to +1 normally. So NDWI also ranges from -1 to +1 normally. Since these variables have a completely different units, they cannot be added directly into the analysis. So therefore, each criteria is reclassified into a common score between 1 and 5. So as you can see, we have divided them into 1 and 5. The 1 is for the low and the 5 is for the near high. So if we go in a more detail from 1 to 5, 1 is a very low hazard, and the 2 is low hazard, 3 is moderate, 4 is high hazard, and the 5 is very high hazard. So this make every data set comparable. And when we talk about their integration, so once every criteria has been converted into the same scoring system, we combine them. The poster shows the distance score plus elevation score, TPI score, NDVI score, NDWI score, and then finally we have the flood hazard index. And the question is why we add them, because this approach is called a weighted equal sum. Each factor contributes equally to the final hazard map. So instead of relying on only one parameter, we combine the influence of all the environmental variables. So this is the final reclassified flood hazard map that we will get. This combined the scores uh, produce the flood hazard index. Finally, the index is reclassified into 5 hazard scores or 5 hazard zones. The first one is very low, then we have low, moderate, high, and very high. The red areas represent the locations with the greatest flood susceptibility, while the blue areas indicate the lowest flood risk. On the right side, the poster summarizes some of the advantages of this methodology. So uses multiple environmental data set, fully reproducible in Google Earth Engine, and many others. You can also read them. We also have a lot of applications for them, like flood risk assessment, urban and land use planning, infrastructure design, disaster management, and many others. You can also use it in different fields. And we have output deliverables like flood hazard map and the raster layers of each criteria and exported geodetics as a 30 meters. So um, now that we have understood the complete methodology and the scientific reasoning behind every dataset and every criterion, it's time to move on to the Google Earth Engine and implement this workflow step by step. We will start with the global surface water dataset and gradually build our flood hazard model until we generate the final flood hazard map. Okay, so we have used first the water dataset that we have already discussed in this posture, and now let's get move into the code. So the first, we have created a variable. We load the water occurrence band from the global surface water dataset and clip it to our study area, so that the only our region will be analyzed. And in this line, we display the water occurrence map. White represent low water occurrence, while the dark blue represent the location where water occur very frequently. So that's how it's gonna work. And then we have some of the permanent water. Like here we identified the permanent water bodies. Pixels with the water occurrence greater than 80% are considered as a permanent rivers or lakes. And then we are just adding the permanent water into the map, and we are just giving it a palette, a rainbow palette. So this displays only the permanent pixels in a blue while hiding all other pixels. So distance for permanent water will be added into there. Okay, next we have the distance hazard score. So we convert the continuous distance values into flood hazard score, like it's ranging from 1 to 5. we have created this variable, and then we have where only distance greater than 3000 and the only distance less than 4000 is 2 pixels farther than 4 kilometers from water receive the lowest flood hazard score. And here is the highest class. So the pixels within 1 kilometer of permanent water receive the highest hazard score because they are more likely to flood. So that's how we are just classifying it to 5 classes based on which parameter have more the highest hazard score. So based on that, we are just classifying it to 5 classes. So first we have created the distance, then we have the elevation data. We load the SRTM digital elevation model and clip it to our study area over here, and we are just adding it to the map. So this will display the elevation map where different color represent different terrain heights. Then we have elevation hazard score. So we are again classifying it to 5 classes, and then we are adding this into the map. So only land pixels are considered for the elevation scoring. We are saying it that high elevation areas receive a low flood hazard score, where very low elevation areas receive the highest flood hazard score because water naturally accumulate here. I think this will make sense to you how elevation gonna work and how elevation is involved in the flood hazard mapping. And then this displays the elevation hazard score map into our map. And then we have created the topographic position index. So TPI compared the elevation of each pixel with the average elevation of its neighboring pixels. And then we have just created this, and we rename it as a TPI. And this will add our TPI layer into the map. Then we have topographic hazard score. So again, classifying the TPI into 5 classes. So the class 1, again, only the land pixels are used for the hazard scoring. Positive TPI values represent the ridges and the hilltops, which have the lower flood risk. So we are giving it as a 1 class, and the 5th class have the very negative TPI values represent the valleys or the depressions, right? So which must receive the highest flood risk score. So the 5th class have the highest flood risk, and the one have the lowest. So that's how TPI scoring gonna work. Then we have the Landsat 8 imagery. So we have created a variable. We select the Landsat 8 images covering our study area. We also have selected a date that is from 2022 first month to 12 month. We have applied the cloud mask function. We have created a median and clip it to our region of interest. And then we are just adding the layers into the map. Okay, then here we assign the easy names to the red, green, and the near infrared bands, making the index formulas easier to read. Then we have calculated NDVI and we have NDWI. Again, the same logic like others, but let's explain it line by line. We calculate the normalized difference vegetation index to measure the vegetation health, and then we added this layer into the map, and we have just classified into the 5 classes. Like we are converting NDVI values to hazard score, where the first class dense vegetation reduces runoff, right? So it received the lowest flood hazard score, and the 5th class sparse vegetation or the bare land receive the highest flood hazard risk. So that's why we have assigned the class 5 value to this. And then we are adding this layer, this NDVI ranked score layer into the map. Then we have NDVI. I have explained all of these indices very much detail in my previous tutorial. So if you have no idea about NDVI and NDWI and how they're going to work and how we can separately calculate them in Google Earth Engine, so you can watch my previous tutorials so that you will get a better understanding of how NDVI and how NDWI will be calculated using Google Earth Engine and how they actually work. So now let's get back to the code, and we have created the variable NDWI. We calculate the normalized difference water index to estimate the surface wetness, and then we have just added this layer into the map. I'm going a little bit faster because we have now the idea of how this code gonna work. So I'm just going through it line by line so that so that this will make sense to you how things gonna work in this code. And then we have the wetness score. How wetness score will work? This is actually kind of we are starting from fifth class. Why? Because very wet areas receive the highest flood hazard risk, and we ended at one. Why? Because very dry areas receive the lowest flood hazard score, and then we are just adding these layers into the map. Then we have the flood hazard. Finally, we have the flood hazard map. So all five hazard layers have added here, and we renamed it as a flood hazard map. And then we are just adding these this final layer into the map. Now we have added all of the flood hazard layer into the map. Now we just want to classify it. So we have also classified the flood hazard score, and how this gonna work is the class 5 where flood hazard would be greater than 15 is considered as the class 5. The flood hazard index is reclassified into 5 classes, so it will be something like very high. Then we have the high, moderate, low, and very low. We are just reclassified into these classes. Then we are adding the flood hazard score into the map, and then we have just added some of the legends that gonna show over here. And this is the function for the cloud masking for the Landsat 8. And if you still don't have any idea for the cloud masking, you can see my previous tutorials where I have explained all of these things in a very detail. And then we have just defined the export functions, like we are exporting our image into the drive. So what I want to export is water occurrence, permanent water, distance from river. I want to export everything. So I have created the code for every index that we're gonna use. Okay, let's just create our the small study area. Now I'm gonna delete this and create it somewhere there near the water, so that so this is my study area. I'm gonna remove the previous one and rename it as region of interest. Enter and run. Now just untick it and let's see the results. Okay, so here you can see the results where we can also see the permanent water and the flood hazard score. Okay, so this was the flood hazard, and this is the flood hazard score. Okay, so here is the wetness hazard score. There is NDVI. Like, you can calculate each and everything using these indices. You can also see the water, the permanent water, distance from permanent water. Like, you can calculate it for the small area and for the large area. So this is how you can calculate the flood hazard modeling using the coding in Google Earth Image.